Geomagnetism. To the casual observer, it is just an invisible force that points north. But for us, as students studying physics, it is a master class in the laws of classical electromagnetism. Today, we're going to analyze the Earth's magnetic environment through the lens of three specific inquiries, bridging the gap between historical navigation and the core principles of our curriculum. Inquiry 1 is on how does the compass actually work. Research into the World Magnetic Model reveals that Earth's field vectors are not uniform. They vary by location, requiring constant calibration, but the underlying physics is universal. My insight here is that a compass needle is a macroscopic magnetic dipole with a dipole moment mu. Looking at our, looking at our textbook, specifically Survey and VUE Chapter 19, we note that any dipole moment in an external magnetic field experiences a torque. This follows the vector cross product equation here below. The needle rotates because the system is seeking its lowest potential energy state. It's a real world proof of the torque equations we've mastered in class. Second inquiry is how is GPS infrastructure protected from the harsh environment of space? NASA's research describes the solar wind as a plasma of high energy protons. Without a shield, these particles would destroy satellite electronics instantly. This connects directly to our curriculum's um, one of our curriculum's objectives, the Lorentz force law. When these protons enter Earth's magnetic field with a velocity v, they experience a force F that is always perpendicular to both their velocity and the field lines. As we study in our magnetic force units, this force acts centripetally, curving the particles into spiral paths. The Earth's magnetosphere is, quite literally, a planetary scale magnetic bottle. Finally, inquiry 3. Why do solar storms break GPS accuracy? Literature confirms that geomagnetic storms compress the mag- magnetosphere, causing the magnetic flux lines to shift rapidly. My insight here is found in Faraday's law of induction. As the magnetosphere is compressed, the magnetic flux through the Earth's ionosphere changes over time. As highlighted in Knight's Physics Chapter 34, a time-varying flux induces an electromotive force. In the upper atmosphere, this induced EMF drives massive currents that scatter GPS radio signals. In the end, navigation isn't just about maps, it's a delicate balance of dipoles, moving charges, and electromagnetic induction. Thank you, and this concludes my research and analysis of geomagnetism.